In this video, I would like to find the antiderivative of x to the n. I want to start with a basic example. Let's try to find the antiderivative of x cubed. Now, my idea is this. I know that if I take the derivative of x to the fourth, I get almost the right thing. The derivative of x to the fourth is 4 times x cubed. And this would be correct, except, of course, for that stupid 4 sitting there. But I can get rid of the 4 on the right-hand side of this equation by dividing by a 4. But if I'm going to divide the right-hand side of an equation by 4, I also have to divide the left-hand side by 4. And what I now want to do is I want to think about what that whole equation has become. The original equation is now equivalent to the equation 1/4 times the derivative of x to the fourth is equal to x cubed, because those 4's, of course, cancel. Now, there's something else that is very important, too. Constants like this 1/4 are allowed to go back and forth across the derivative operator, so the equation that we're looking at can also be written as take the derivative of x to the fourth divided by 4, and that will be equal to x cubed. And let me clean up my handwriting just a little. And so what this last equation is saying is that if I let capital F of x be equal to x to the fourth over 4, then capital F prime of x will be 4 times x cubed over 4. Those 4's cancel out, and I get an x cubed. And because of that, I can write the antiderivative of x cubed will be equal to my favorite antiderivative, the one that I just found, x to the fourth over 4, plus any constant of integration that I care to add. Now, in this particular statement, there is nothing special about this 3. It's the relationship of the 3 to the 4 in the answer that's important. In other words, we can generalize the work that we just did in this specific example to get the following basic formula. So in general, if I want an antiderivative of x to the n dx, I'm going to add 1 to the exponent to get x to the n plus 1, but then I will have to fix the answer up by dividing by that new exponent, and then I will add the constant of integration. Now, I want to stare at this formula for just a minute. I can only do this formula if the original exponent is not equal to -1. If the original exponent is equal to -1, I would be dividing by 0 here, and I can't divide by 0. So that's where this restriction comes from. The reason this formula works is that we can take the derivative of our answer, and when we take the derivative of the answer, we're going to get the derivative of x to the n plus 1 divided by n plus 1, plus the derivative of that constant, and the derivative of this chunk is going to be an n plus 1 times an x to the n divided by an n plus 1, and then we're going to get the derivative of a constant is a big fat 0. And when we look at this, those n plus 1's cancel, and we are left with an x to the n. So this formula works as long as n is not equal to -1. Of course, that raises the question, what happens if n is equal to -1? So let's find the antiderivative of x to the -1. Well, in order to do this, the first thing that I want to do is I want to think about what exponents are. I can rewrite that x to the -1 as a 1 over x. And this gives me an immediate idea. I want to recall that I know that the derivative of ln of x is 1 over x. And using this fact here, so using this fact, I can say that the antiderivative of 1 over x is going to be the natural log of x plus any constant that I want to add. So to summarize what we've done, we've established this important fact. If I want an antiderivative of x to the n, it breaks into two cases. The antiderivative will be x to the n plus 1, divide by n plus 1, plus add any constant that you want to, as long as n is not equal to negative 1. And if I'm looking at the antiderivative of x to the n and n is equal to negative 1, I get the natural log of x plus any constant that I want to add. And this is true when n is equal to negative 1.